In this episode, we will implement a method to handle collision callbacks, as well as introducing collision layers. We'll also implement an extremely simple entity system. This will not be the entity component system paradigm. We may implement something like that later. If you'd like to know more, I have a video about ECS that gives an explanation and a simple implementation. I just want to reiterate that this engine is designed specifically for the type of game we're making, which is an arcade-style platformer. Most of what you've been and will be learning is about implementation details of such a game, rather than a general purpose solution. If you've been enjoying the series, please leave a like on the video as it does help me a lot. Make sure to click subscribe and hit the bell if you don't want to miss future episodes. Now let's get into it. Now first up, we're going to create the simple entity system. In a strange twist, let's edit the build script first instead of last. As with the other modules, just create a new variable called entity, and then output it on the files line, and we're done. Now we'll create a entity.h file in source engine, and we'll create an entity.c file in source engine entity.c. Head into the header file. In here we just need an entity struct that has two fields. The first is a usize to hold our body ID, and the second is a boolean called isActive. Now the reason we're using a boolean instead of using, for example, two arrays, one for active entities and one for inactive entities, or just removing something from the array and reorganizing it, is because we're actually using the indices of the array as the IDs. So if we remove something from the middle, then suddenly all of the entities after that one are going to have the IDs invalidated. It's not the most efficient solution for larger games, but for our small game, I don't think we need anything more fancy. Next, we'll define our function prototypes. Entity init. In the same vein as other modules, this will initialize any module's state. Entity create. This function takes 5 parameters and returns an index. Position. The position of the axis-aligned bounding box associated with this entity. Size. The size of the AABB, not the half size. Velocity. The starting velocity of the body. Collision layer. This unit's collision layer. We'll set those up soon. Collision mask. The mask for which layers this entity should collide with. I'll explain that later. And we'll just define 2 more functions here, entity get and entity count. Copy these prototypes over to entity.c. First up, we need somewhere to store our entities. For this, we'll just use an array list like we have been in the other modules. We'll make it static so it's only visible inside this C file. Entity init will just initialize the list. Entity create should look very familiar. It's the same type of initialization function as the one in the physics module. I want to explain some changes that we'll be making to the create functions in the physics module. The way it works right now, you create a body and pass in just a position and a size, and you get back an ID. Then you need to query the physics module to update any other fields that exist. However, almost all of the time we want to create a body that has other fields filled out, like velocity. And after this episode, collision layer and collision mask. So our function signatures going forward will be designed to handle the most common case rather than a minimal case, as they have been. Alright, entity get and entity count are just getters, as I said. The reason we're using getters here rather than giving direct access to the entity storage list is so that implementation of the entity storage can change without updating the gameplay code. Alright, moving on to the physics module. We first want to update the function prototypes, as I was saying. As discussed, we'll just add parameters to handle the most common case. Our game is an arcade-style platformer. The only bodies that are created is the player, some enemies, and collectible crates. So the most common entity to be created will be the bullets, followed by enemies. I forgot to mention bullets. Both of these use cases require velocity, so we'll add that parameter. And every body, regardless of its use, will make use of a collision layer and a collision mask. So we'll add those too. And I'll explain those in a moment. To get the collision data back from the physics system, we'll use a pattern that should be familiar to you if you've used something like Unity. We're going to create some function pointer types, but before that, we'll need to move the struct type defs to the top of the file. Now we'll create 2 function pointer types. onHit and onHit static. Then on the body struct, we'll add fields for them, as well as collision layer and collision mask, which I will explain soon. We'll need to add the collision layer to the static body struct, but we won't add a mask or any callbacks. While we're here, our hit struct is going to need a bit of extra data too. a field called other ID that stores the ID of the body that's being hit. This will be important later. The way we're going to filter out collisions between different layers is by using something called a bitfield. If you already know about bitfields, skip to the next section unless you want a refresher. To understand why this is a useful approach, let's look at another way you might do this first. One way you might approach this problem is by assigning a collision layer like we have done, and then adding an array of booleans that represent the layer indices that this one can collide with. Check if one body can collide with another, we can just check the index of the layer that B is on is true in the array of A. This is already pretty simple, but it does waste an awful lot of space. That doesn't matter for our game, but it's important to understand what kind of memory footprint your structures have if you want to create larger projects. In this simple example, we're using 8 bits for the collision layer and 8 bits per boolean for a total of 72 bits. So how can we do better? Well, let's take a look at what a boolean looks like in binary. As you can see, we're using just 1 bit of the memory that a boolean takes up to determine whether it's true or false. We can actually use all 8 bits of this memory as 8 different boolean values. This is what a bit field is. Most programming languages, including C, come with operators designed specifically to deal with bits. The only ones that we are interested in exploring today are the OR operator, the AND operator, and the shift left operator. AND and OR act predictably the same as their logical counterparts, but compare bitwise instead. Let's look at a few examples. The OR operator will produce a 1 where either input has a 1. I've stacked the numbers on top of each other so you can more easily see the comparison. Reading from the left, the first 3 bits of both inputs are 0. So then the output of the bits are 0. The 4th bit is a 1 in the second input, so the 4th bit from the left in the output is 1. The 5th bit in both inputs is 1, so the output is 1. And finally, the last bit of the first input is 1, so the output is 1. Keep in mind that we are reading from left to right, but that is actually backwards. It's just what we're used to in English, so I read it that way. Now we'll take the same numbers and use the bitwise AND operator. This will return 0 where either bit is 0 and 1 where both bits are 1. The last operator we want to look at is called shift left. It will shift the bits to the left by the number on the right, in this case 1. So if we have a body with this collision mask, we can check whether it collides with another body by using the bitwise AND operator. If the value is anything other than 0, then we have a match and we can check for a collision. All of this may seem more complicated, but it's actually about the same amount of complexity once you understand the bit field. As well as that, the amount of storage required for the original method is 450% of the storage required for the bit fields. Alright, now that's over, we can move on to refactoring our collision code to use them. We're going to have callbacks when a regular body collides with either another regular body or a static body. Now so far we only have collision detection on the regular versus static, so we're going to have to update our code a bit. Rather than duplicating the code, we're going to move some sections into their own functions. Basically what we want to do is everything inside the sweep static bodies loop, but again for regular bodies. Naturally, the best thing to do here is to move the code into a separate function and then pass in the parameters we need. Let's create a function called update sweep result. Rather than creating 2 code paths, one for regular and one for static, we can instead just pass in the parameters we need for both types. We'll pass in a pointer to our result hit so that it can be updated when the conditions are met. We also need to pass in the other ID so that we can later get the pointer to the other body for the callback function. To calculate the hit, we need the AABBs and velocity. Then to filter out the collisions based on layers, we need the collision mask of A and the collision layer of B. Code is pretty much the same as the inner loop from before, but we do a check for the layer at the top and assign the other ID if there was a hit. Now we want to add our function to sweep the regular bodies. You can copy and paste the sweep static bodies function, change the list to body list, change the type from static body to body, use the correct function, and also add a check to make sure we don't check bodies against themselves. Down in sweep response, we'll define a new hit variable called hit moving and call our new function. Since we don't do any collision response with the body versus body, we just check to see if the body has an onHit function and then we call it, passing in this body. Pass in the other body, this is where the other ID comes in handy, and the hit. Down in the static response, we do the same thing, but the static version. Finally, we'll just update the create functions to match their new prototypes. Hello there, this is the editor. Just make sure that you add the velocity 0 and velocity 1 here, as I made a mistake during the initial recording. Over in main.c, include the entity header, and we want to define our collision layers. You could just memorize which bit is which layer, but I find it's easier to create an enum for this. The first layer will be all zeros, and then a 1 at the end, which is just the number 1. Then to get the number 00000010, we can use the bit shift left operator. Then we just repeat that for each layer. So in a U8, this will give us a total of 8 layers. But if you want more layers, you can just change the masks and the layers to a U16 or a U32 or a U64. Next, we'll define a couple of variables that will be useful in the demonstration. Player color and player is grounded. In our input handle function, we'll update the jump code to check that the player is grounded, and then set the player is grounded variable to false. Next up, we'll define our collision callback functions. These are the ones which we'll pass into the create functions shortly. For our player, when it hits another entity, just want to change the color of the player for now to see that it's working. So we'll set the red channel to 1 and we'll set the blue channel to 0, and that will make the box show up as yellow instead of cyan. Next, we'll define our player's static callback. In this case, we just want to check the normal direction, and if it's on the ground, we'll set grounded to true. Finally, we'll create one for our enemies, which we'll create shortly. In our game, the enemies are always moving and they always turn around when they hit a wall. So we can set that up really simply by checking the normals and then setting the velocity. Down in main, make sure to call the entity init function. Then we'll define our common collision masks and use the bitwise OR operator to combine the layers into a mask. Enemies will collide with the player and the terrain, and players will collide with the enemies and the terrain. Then we'll create a player entity instead of a body, and we'll pass in the required arguments. Next, we'll update the static body create functions with the collision layer terrain. Finally, we want to create a couple of other entities. For these, we'll pass in the enemy mask and the enemy on hit static callback function. Alright, we're almost there. Down in the main loop, we'll get a reference to our player and its body, and then we'll swap out the cyan for our player color variable. We need to render the two enemies we just made. Finally, after rendering, we'll reset the player color to cyan. And that's it for this episode. If all went well, then you should have a player that can jump around, but only when it's on the ground, two entities moving back and forth on the screen, and then your player should flash yellow whenever it interacts with only one of the entities. Thanks for watching, and I'll see you in the next one.